These slides are about electric field. The electric force, which is a field force, is introduced so far. A field force can act through space, producing an effect even when no physical contact between the objects occur. An electric field is said to exist in the region of space around the charged object. When another charged object enters this electric field, an electric force acts on it. As an example, which shows a small positive test charge Q0 placed near second object carrying a much greater positive charge Q. We define the strength, in other words, the magnitude of the electric field at the location of the test charge to be the electric force per unit charge, or to be more specific, the electric field E at point in space is defined as the electric force Fe acting on positive test charge Q0 placed at the point divided by the magnitude of the test charge. That is, E equal to Fe divided by Q0. The vector E has the SI unit of newtons per coulomb. Note that E is the field produced by some charge external to the test charge. It is not the field produced by the test charge itself. Also note that the existence of an electric charge is a property of its source. For example, every electron comes with its own electric field. We say that an electric field exists at a point if a test charge at rest at that point experiences an electric force. Once the magnitude and direction of the electric field are known at some point, the electric force exerted on any charged particle placed at that point can be calculated from E equal to F divided by Q0. The electric field magnitude for various field sources are given in table. When using the equation of electric field, we must assume that the test charge Q0 is small enough that it does not disturb the charge distribution responsible for the electric field. If a vanishingly small test charge Q0 is placed near uniformly charged metallic sphere, as in the figure, the charge on the metallic sphere which produced the electric field remains uniformly distributed. If the test charge is greater enough that is Q0 prime is much greater than Q0, the charge on the metallic sphere is redistributed and the ratio of the force to the test charge is different. So F prime divided by Q0 prime will not be equal to F divided by Q0. To determine the direction of an electric field, consider a point charge Q located at distance r from a test charge Q0 located at a point P. According to Coulomb's law, the force exerted by Q on the test charge is given by Fe equal to Ke Q into Q0 divided by R square into R, where R with cap is a unit vector directed from Q towards Q0. Because the electric field at P, the position of the test charge is defined by E equal to Fe divided by Q0, we find that at P, the electric field created by Q is E equal to Ke into Q divided by R square into R. If Q is positive, the electric field directed radially outward from it. If Q is negative, the field is directed toward it. To calculate the electric field at point P due to a group of point charges, we first calculate the electric field vectors at P individually and then add them vectorially. In other words, at any point P, the total electric field due to the group of charges equal to the vector sum of the electric fields of the individual charges. This superposition principle applied to fields follows directly from the superposition property of electric forces. Thus, the electric field of group of charges can be expressed in the given equation.